Friends, we will continue the discussion on the rings and chain links. We did an example problem on closed rings under axial tensile loads. In this lecture, we will derive the equations to find the stresses on chain links, and we will derive the equation to determine the bending stresses and also do a numerical example to estimate bending stresses or total stresses in the intradas and extradas of a chain link under the given loads. In opening remark, we can say that chain links are treated as thin, extended closed rings. A typical chain link looks like this. So, it has got two components. This is the straight component and this is the curved component. Let us call this distance as L and let us call this radius as R. Let us say the link is subjected to an axial force, tensile force P as shown in the figure. Let us take a segment of the ring and the link, which I am showing here. Say this is my R subjected to loads P by 2 and moment m0, where moment m0 indicates increase of radius of curvature in the given section. So, as I said, they have two sections. One, the straight portion where MB is simply m naught, and for the curved portion bending moment is at any section as shown below. In fact, let us extend this further, close it here. This is p by 2, this is m 0 let us say this is r and this angle is theta and this distance is actually r minus r cos theta subjected to p by 2. Therefore, m b is m 0 minus p by 2 r minus r cos theta. So, as per Castigliano's theorem, the strain energy partial derivative should be set to 0, which now indicates that strain energy for the straight portion plus strain energy for the curved portion should be set to 0. So, the strain energy total is actually 4 times of 0 to L m by E I, because m is m 0 in the straight portion and dou m 0 by dou m 0, which is d s, that is the straight portion, plus curved portion segments 0 to pi by 2, 4 in number. The moment in this case is going to be m b, therefore, m b by m 0 and d s, and that should be set to 0. Okay, equation 1, which implies that 4 times 0 to L m 0 by E I d s plus 4 times pi by 2 m b by E I d s, which indicates 4 m 0 L by E I plus 4 r by E I 0 to pi by 2 m 0 minus p by 2 r minus r cos theta d theta, which implies 4 m 0 by E I plus 4 r by E I m 0 theta minus p r by 2 theta plus p r by 2 sin theta 0 to pi by 2, which implies 4 m 0 L by E I plus 4 r by E I m 0 pi by 2 minus p r by 2 pi by 2 plus p r by 2, which should be set to 0, which implies m 0 L by E I, because this 4 can get cancelled, plus m 0 pi r by 2 E I minus p r square pi by 4 E I plus p r square by 2 E I, which can be set to 0, which indicates m 0 L plus m 0 pi r by 2 minus p r square pi by 4 plus p r square by 2 set to 0, which implies m 0 2 L plus pi r is equal to p r square by 2 minus 1 plus pi by 2, which implies m 0 by 2 2 L plus pi r. Let us do it like this, m 0 is equal to p r square by 2 pi minus 2 by 2, equation 2. Interestingly, we can make a comment at this point. It can be easily seen that at L equals 0, equation 2 reduces to m 0 pi r by 2, which is p r square by 2 pi minus 2 by 2, which means m 0 is p r by pi by 2 minus 1, which is same as the earlier case of a closed ring. L by 2, L is 0 means indicated a closed ring. We get the same equation as we derived in the last lecture. Further, please note that m 0 produces tension at intradas and compression at extradas. Now, we can write a general expression for bending moment at any angle theta is m b, which is m naught minus r by 2 r minus r cos theta, which gives me m b is p r square by 2 pi minus 2 by 2 L plus pi r minus p r by 2 1 minus cos theta. Let us interestingly ask a question. Let us say this is my L, this is my section BB, this is my section AA, and this is my distance r at theta. So, at theta equals 0, bending moment at BB will be given by m 0, which is simply p r square by 2 pi by 2 L plus pi r. At theta equals pi by 2, maximum bending moment will occur at AA and is given by m b equals p r square by 2 pi minus 2 by 2 L plus pi r minus p r by 2. That is called equation number 4a and 4b. If we really wanted to find the combined normal stresses across this section, then we should use the equation m b by a e y plus or minus e by y plus or minus r plus p by 2 a cos theta. This positive indicates that direct stresses are tensile and tensile is positive. Now, for design guidelines, of chain links, let us say this dimension is L and this is R. Usually it is circular in cross section. So, R be the radius of circular cross section, capital R be the radius of curvature, small r is this, L length of the straight section, as shown. So, R by R usually varies from 0.2 to 0.5 for an effective design, and L by R usually ranges from 0 to 4, in sense a closed ring to a link. Now, interestingly, when the stresses in the links are more than permissible, there are two ways of correcting it. One, increase the diameter of the cross section. Alternatively, introduce what is called as a central stud. So, central stud is a very interesting component which is introduced as shown in the figure now. This is called central stud. So, the ring or the link is reinforced with a central stud in case the stresses at any section increases permissible limits. Now, we will take an example problem and try to find the stresses. Let us say the problem is like this: a chain link shown in the figure is made up of 50 mm diameter rod and it is circular at one end. Mean diameter is 100 mm. Straight sides of the link are 80 mm. the link is loaded by 100 kilonewton axial pull. Let us see the figure. So, we know that this length, which is actually 2L, okay, or we use say capital L, which is 80 millimeters, and this distance is 100. Therefore, this distance is going to be 50. This is subjected to a pull of 100 kilonewtons. Let us write down certain data necessary for the numerical. R is 25 mm, that is radius of the cross section, because the diameter is 50 mm. Radius of curvature is 50 mm. Ri is 50 minus 25, which is 25 mm. Ro is 50 plus 25, which is 75 mm, and 2L is now for the curved part we need to find the E value. So, to determine E, that is shift of neutral axis from the centroidal axis for the curved part. We know the equation E is given by r minus r square by twice of r minus root of r square minus r square. Let us substitute 50 minus 25 square by twice of 50 minus root of 50 square minus 25 square. I will get this value as 3.349 millimeter. Positive indicates that neutral axis shifts towards the center of curvature. MB at any section at an angle theta is given by MB is PR squared by 2 pi minus 2 2L plus pi r minus PR by 2 1 minus cos theta. We already derived this equation. Let us substitute 100 kilonewton. So, newtons, r is 50. So, 50 square divided by 2 pi minus 2 by 2L is 100 plus 50 pi minus PR by 2. So, 100,000 is my P, R is 50 by 2 into 1 minus cos theta, which is 55 44 74.7 minus 25 10 power 5 1 minus cos theta. Now, at theta equals 0, MB is 55, 44, 74.7 Newton millimeter. I want to now find the direct stresses, which is P by 2a cos theta at theta equals 0, normal stress or direct stress is simply P by 2a, which is 100,000 divided by 2 of 25 r square. So, pi r square, which is plus 25.47 Newton per mm square, plus indicates it is tensile. Now, I want to find the bending stresses. So, now cross section is circular. This is my OO axis, let us say. This is my CG. So, centroidal axis. This is my neutral axis. This distance is E, and E is 3.349 millimeter, and this distance is R intradas, and this distance is R extradas, and this distance is R, which are all known to us. So, what I want to know is the distance of the extreme inner fiber and the distance of the extreme outer fiber from the neutral axis to compute the bending stresses. So, I should say y I is R minus E, which is straight away 25 minus 3.349, which is 21.651 millimeter, positive because E makes a shift towards the center of curvature. And similarly, distance of extreme fiber extradas will be R plus E, which is 25 plus 3.349, which is 28.349 millimeters. Once I know this, I can easily compute the combined stresses at intradas and extradas at section BB, which is theta equals 0. So, sigma intradas is plus 25.47 plus MB, that is 55, 44, 74.7 by AE, which is 25 square pi into E is 3.349 multiplied by distance of extreme fiber inner by Ri. Similarly, outer will be plus 25.47 minus 55, 44, 74.7 divided by 25 square pi 3.349 multiplied by 28.349 by 75. Please note, friends, this value will be negative. Now, this value is plus 98.5 Newton per mm square, indicating it is tensile, and this value is minus 6.40 Newton per mm square, indicating it is compressive. So, friends, we have interestingly estimated the equations or derived the equations for bending stress in the chain links at any section. We have used the conventional equations for curved beams, which we have derived in the last set of lectures. We have also used an example problem to assess the stresses in interdas and extradas of a chain link with a numeric example. We have also understood certain elementary design guidelines to choose the geometric dimensions of a chain link, and chain links are very common and being used in the mooring lines in offshore structural systems, even for anchoring semi compliant, compliant or fully floating vessels in the sea. I hope, friends, these set of lectures what we are discussing in module 2 under the coverage of advanced structural analysis are helpful and address certain special kinds of problems and estimating stresses in cross section under certain special applications, which will be very useful and which is essential in case of offshore structures under special loads. Thank you very much.